Hello, my name is Ava Bird, and this is my lab report for Physics 2212, Lab 3, the magnetic field of a bar magnet. The purpose of this lab was to get a better understanding of magnetic fields and how the distance away from a magnet affects the magnitude of a magnetic field, specifically on axis and perpendicular to the axis. The main model we will use to do this will be the PHYS law, as seen here, but we will also use distance dependence functions of a magnetic field, as seen here. I will briefly summarize the procedures used in the lab. First, I determined Earth's magnetic north by rotating my phone until the x component on the magnetometer is equal to 0. I did this so that the magnetic field values were only coming from the bar magnet and not Earth. Then I set up a meter stick perpendicular to the magnetic north with the bar magnet at one end. Then I located the magnetometer chip in my phone, and to do this I slid my phone in the x and y direction until the readings were maxed out for both values, which gave me an idea of where my magnetometer chip was. Then I moved my phone at various distances along the meter stick, or on axis, for specific magnetic field values. I also did a similar procedure to get the magnetic field measurements for a direction 45 degrees to the magnet. Through these processes, I recorded my data, which I will use to compute values in my code, which will be seen in the future. So now on to the models. As I mentioned before, I used the PHYS law in this experiment, which is a formula for the magnetic field dependent on the magnetic dipole moment and an observation vector. This law was mainly used for the code. I will also use formulas for distance dependence, which were mainly used to calculate k, constants in the magnetic field formula, n, a constant that determines how much distance affects the magnetic field, and mu, the magnetic dipole moment. Here's the data that I got when I conducted the on-axis portion of the experiment. I then transformed the data to a linear equation, as seen down here, from this equation here to this equation, using natural log to do this. And so, by doing that, I was able to graph my measured data and find a line of best fit where the slope is equal to n, which was negative 3.213. Since the expected n value was negative 3, my data got fairly close to the expected value that we were supposed to see. The y-intercept was equal to ln of k, as seen here, which was negative 14.828. By expanding out k, I was then able to calculate mu, as seen at this part, which was 1.81657 amperes per meter squared. As for the off-axis data, the average value of d perpendicular was 0.183, and the average magnitude of b net was 0.0001825. The measured b value can be seen here, which was negative 0.00017, 5.38 e to the negative 5, 3.087 e to the negative 5, and this we will compare to our calculated value that we'll see in the code. But first, let me walk you through my code. So the purpose of my code was to calculate and visualize the magnetic field of the bar magnet computationally. To do this, I started by writing a function that would calculate a magnetic field due to a dipole at the location according to the PHYS law. This can be seen here. I then created a visualization of the magnetic field by determining 2 on-axis positions and 4 perpendicular positions compared to the bar magnet. Computed the magnetic field at these points using my function that we just saw, and then visualized them using GlowScript. I also visualized the magnetic field at a point 45 degrees to the bar magnet, which can be seen at the last part right here. So at the top, these are my vectors. Here is the on-axis calculations, and then below that is the perpendicular calculations. And then I created visualizations of magnetic field here. And so one interesting observation that we can see from my values is that the on-axis values have a magnetic field magnitude 2 times that of the perpendicular locations, even though they are the same distance from the bar magnet. This is similar to how with electric fields work with on-axis and perpendicular dipole formulas too. Now that I've calculated the magnetic field using GlowScript, you can see that the calculated values of my magnetic field and the measured values are very different, as you can see here. And now onto the conclusion questions. Now if I hadn't accounted for magnetic north in my experiment, all of the data would have been skewed by the Earth's magnetic field in the direction of magnetic north, which means that the x component would not have been equal to 0 at the start of our experiment, which in effect would have made my values for k, mu, and n not accurate. In addition, the second question, if I had stuck two identical magnets together, the direction of the magnetic field would be the same, but the magnitude would approximately double. From this lab, I was able to understand distance dependence of magnetic fields and calculate the magnetic dipole moment. Thank you.